All right, so I'm actually going to go back a slide or two real quick. So yesterday I showed you this slide right here. I told you there are 5 ways to calculate delta H. Remember, calculate means to quantify, right? No, this is actually really important. So again, this means to quantify. So today we're going to try to get through at least 2 of them. We're going to try to get through stoichiometry and calorimetry. So let's go ahead and look at stoichiometry. We looked at that yesterday, so here is where we're going to start. So determine stoichiometrically the physical states of all reactants and products must be specified. Notice what's in bold and in blue. Peyton, read that again in bold and blue at the top.
Must be specified.
What must be specified?
The products.
The physical states of matter must be specified. So if you notice something, let's look at this. So the first one is water going from what to what? The second one is water going from liquid to gas. Do they have the same delta H values? No. My first question is, are these numbers positive or are they negative? They're both positive. So here's a little point of emphasis that I want to make. Since they are both positive, what does that mean about both of these reactions? They are endothermic. Now, let's talk about how you would know that, even if you didn't know. So first of all, solid to a liquid, closer together or farther apart? Farther apart. To separate something, what has to happen to energy? It's got to go in. It's got to go into. Well, if it's going in to separate, then that's endothermic. Okay? Liquid to gas, closer together, farther apart. Farther apart. So again, energy's got to go how? In. Well, think about this, and this is an important question. What if I take this reaction, the top one, from a solid to a liquid, and I flip it? What happens to that thing? It's the same number, but it's opposite. Okay? So here's something really weird that always throws students off. Going from a liquid to a solid is what process? Liquid to a solid. Freezing. Freezing. Freezing, freezing, freezing. But you just told me, again, this is backwards, right? So going from here to here is backwards. So what happens to the sign of delta H? It turns negative. What type of reactions are negative delta H's? Exo. When you think of exo, you think of what temperature change? Hot. But we're making ice. How does... Exactly. Okay? So it's a weird thing. So just because something might get cold in a sense doesn't mean it's necessarily an endothermic reaction. So keep that in mind as we go throughout this. Okay. So why is the L to G so much more than the S to L? So again, if you notice, do you agree that the L to G is 44, the S to L is 6? Why is the liquid to a gas more? Very good. It takes more energy to separate a liquid to get it to a gas. Very good, okay? So if you want to write that in, it may be a good idea. So here's the stoichiometry part of this, and we're going to do this quite a bit. How much heat is evolved? Remember I told you about that word yesterday. What does that mean? Released. So you have to have what type of sign here? Negative. That's going to be very crucial to this. What happens when 266 grams of white phosphorus is burned in air? Now let me ask you, what type of reaction is this? It is combustion. But why does it look weird from anything that you've ever done before? There's no hydrocarbon. So this was the thing that I told you. I said, remember a long, long time ago, I said, all combustion reactions do not have to have a hydrocarbon. But what does have to be present? The oxygen has to be present, and it has to produce some sort of oxide. Was an oxide produced? Yes. Here's throwback. Do not say this out loud. Write it down somewhere around this. Write the name of that last formula. See? What is the name? What is P4? Well done, an allotrope. I want to see if you guys remember how to write this stuff. Perfect. That's exactly what I forgot to tell you to do that, so thanks. Where's the separate stack? Right here. Awesome. Okay, James, what you got? Shh, James. Shh, shh, shh. Cody. Shh, shh, shh. Sarah. It's not Sarah. Samantha. Yeah, what's the name of it? Speaking of which, Samantha, totally off topic. Your black folder is over here on that counter. Devin. P4010. Chase? That's what I said. Name it. Deck oxide. Very good. Tetraphosphorus deck oxide. Shh. Stop. Y'all, this, you got to go back over there. This can't. No, this can't. I know, but you can't, because you're going to argue back and forth all the time. Stop. All right, so here's the deal. 266 grams. Now, notice what it said. Look, when 1 mole of phosphorus, when P4 burns, it gives off negative 303 kilojoules. But is 266 grams 1 mole of P4? No, it's not. So this is what we've got to do. So I don't think you have this written, right? So start with 266 grams of P4. I think you have to write this down. 266 grams of P4. Now, if you want to, what's the question? What are we trying to get? How much heat is evolved? Okay. So if we have grams, what's the first thing we got to get to? Moles. All right. So do your next step. Now, where in the world did that 123.9 come from? The molar mass of P4. You just take whatever mass, whatever P is, which I can't. The mass of P is 30.97 times 4. I know, I'm just saying, but that's where the 123 came from. 37.94 times 4. Now, we've got 1 mole of P4. So here's the deal. If I want to get rid of moles, where does it have to go? It's got to go on the bottom. And again, what energy unit am I trying to get it in? I'm trying to get it joules or kilojoules, right? Well, there's a problem with this. Remember, all delta H reactions must be kilojoules what? Per mole of reaction. That's why we now have to use that per mole thing. So can you use another stoichiometric step here? That is the step that you have to do. That's why, if you did not know, it was negative 3013 kilojoules per 1 mole, then you wouldn't know how to do this. Yes, you have to have delta H to do this. It's supposed to be negative. It's a typo. It is supposed to be negative. You can go from grams to joules or kilojoules, yes. This is what, remember what we said, we're trying to calculate delta H. But here's the problem, Devin. How much P4 did you start with? 266, Devin. But how much is 1 mole of P4? 123. Well, 1 mole gives off negative 3,000. Did you start with more than a mole or less than a mole? You started with way more than a mole, right? So should you have more than 3,000 or less than 3,000? You should have more than 3,000. So that's what we're trying to figure out is we didn't start with exactly 1 mole of phosphorus. We started with 266 grams of phosphorus. So we got to figure out, because we have more than 1 mole of reactants. Well, it's going to be more than 3,000. So once you do this, you should run the numbers and find out it comes up to be unit cancellation. Now, again, it's supposed to be negative. It is a typo. It's supposed to be negative 6,470. Now, again, kilojoules, do you have per mole of reaction on this one? You do not on this one. Why? It's just how much heat's being given off. It's how much energy is being evolved. Okay. It is supposed to be negative. Yes, that is a typo. Logan, go ahead. It is negative. Yes, that is a typo. Yes. Because energy has a unit of joules or kilojoules. Because heat is different than energy. Heat is a transfer of energy. How much? Well, it really technically should say energy here. Pretty much heat and energy, because they're the same thing, kinda, in a weird, strange way. All right, so now see if you can calculate this one and read how it's worded. This one's a little different than the last one we just did. No, I take that back. It's not different. It's different compounds. All right, so my question is, where do I start? 5.8 grams. I'm going to change pages because it takes forever to write on that page. All right, so I've got 5.8 grams of CH4 So CH4. All right, and we said it was 16.05 grams in 1 mole. And then in 1 mole, how much heat was utilized in 1 mole? Notice this was typed a very efficient way because it says when 1 mole of methane is burned at a constant pressure, 890 kilojoules per mole of energy is what? So what does that tell you? It's negative. Very good. So you have to make sure that you include the negative 890 kilojoules. Now here's the one thing I want to talk about. How much methane did you start with? You started with 5.8. How much is 1 mole of methane? 16.05. So did you start with more or less than 1 mole? Less than a mole. So did you have more or less than 890? You should have less than 890. So when you calculate it, what should be your answer? -3. That's actually a good question. How many sig figs were given right here? Well, it's the least amount, remember? Technically, it says 890, so that's 2 and that's 2. So let's go with 2. So 320. Okay, negative 320 kilojoules. Okay, negative 320 kilojoules. Make sense? Okay. Carla, you good? You good? Samantha, you good? Yep. Chris, good? Okay, all right. Let's go to the next one. So here's a different way to look at it this time. Okay. So sample problem A. Upon adding solid potassium hydroxide pellets to water, the following reaction takes place. Now this is true. We're actually going to do this. We're going to do this potassium hydroxide. It's hand warmer activity. So solid potassium hydroxide, what does it turn in? What states of matter does it go from and to? Solid aqueous. So what does that tell you about potassium hydroxide? It's soluble. What is aqueous potassium hydroxide? What kind of base? It is a strong base. Very good. So that's how you can get strong bases. Now, notice how this question is written. It's a little weird. And every year this confuses students. That red underlined part is not the delta H. It's a product, which means it's what? It's exothermic. Every year students kind of get confused by this. Is they see the plus sign and what do they assume? It's positive, which means it's what type of reaction? Endo. Guys, the only way that if plus or minuses matter is when it says delta H equals. This is actually a part of the reaction. Okay? So answer the following questions regarding the addition of what? 14 grams of potassium. Does the beaker get warmer or colder? Why? Exothermic. The beaker gets warmer. Think about this. When you drop those pellets into water, right? Because that's how it's going to turn into aqueous, right? Is that what aqueous means? Okay. When it turns into water, what's the first thing that has to get warm first? Well, that was redundant. What's the first thing that has to get warm for the beaker does? The water has to warm up. But how is the water warming up? What are these things? What's the pellets doing? When technically they're not breaking down. They're technically forming bonds. Okay? So when they form bonds, they're going to release all this energy. And so what's going to be there to absorb all that energy? The water is. Well, if the water warms up, what does the glass do? It also warms up. Okay? So number 2, is the reaction endothermic or exothermic? Well, we've already talked about that. Technically, these questions should be reversed. Are they reversed on yours? Or are they like this? Okay, so you know it's exothermic because I told you that in the beginning. And then finally, what is the enthalpy in kilojoules per mole of reaction change for the dissolution of 14 grams of potassium hydroxide? So do what you just did a few minutes ago and calculate the delta H for this. Calculate the delta H for this. I will tell you this. The molar mass of potassium is 39.1. Potassium is 39.1. You should be able to do the other part. 39.1? Yeah, 39.01. No. 0.1. 39.1. perfect. Yeah, that'll work. What I'm actually going to do? Yes, in by Hall. All right, so let's flip over. So I've got 14. You've got it right there in front of you, Peyton. Why are you freaking out? So you've got 14.0 grams of KOH. Okay? So I've got grams of KOH. I got to go to moles of KOH. And then I've got to do 1 mole of KOH. It was, now is it plus or minus here? Negative 43 kilojoules. Okay? So over here we've got 1. So 39.1 plus 16 plus 1. So it's 54 even, right? No. 56.111. That's right. 56.111. So, whenever you do this, your final answer is going to be what? Now, real quick before I ask, we started with 14 grams of potassium hydroxide. 1 mole was 56 grams. Well, if 1 mole puts out negative 43, did you start with more than a mole or less than a mole? Less than a mole. So your answer should be less than 43 or more than 43? Less than 43. Was it? What was it? Negative 27.1. Will somebody give me the real answer? I mean, I'm to the point now where it's just... Yes, sir. Yes, and here's why. Right here, it says, what is the enthalpy in? You see what I'm saying? So if it ever tells you the unit, use the unit. No, that's not it. That's Hess's law. For the change in the dissolution of 14 grams of potassium. So that's this whole thing. No. This is how much 1 mole gives off. So we started with, that's the wrong button. We started with less than 1 mole. We started with 14. So that's why 56 and 43 are related. But 14 is related to 10.7. I don't know if I'm following your question. I understand that. The change in, it's if you had 1 mole, you'd had 43. But you didn't have a mole. You had 14, so you had 10. So you dropped from 43 to 10. Does that help? Devin? Yes, sir. Yes, sir. All right, that's a good question. Do you see how that this is a product in the reaction? Exactly. If heat's on the product, it's an exothermic reaction. Samantha, does that help? Is that what you're going to ask? Very good. It's a good question. I'm glad you asked that. Again, I want to say that one more time. The way you know that this is exo is because when heat is a product, it's exothermic. So, Devin, how can I rewrite this to make it an endothermic reaction? Move it the other side, and I would have colored it blue. Okay? I'm sorry. My bad. Go ahead, Brianna. Because it's technically asking you to calculate the enthalpy. And here, I'm going to be honest with you. I think I messed up on these because it said calculate delta H. The previous 2 problems we did should have also been per mole of reaction. So that's my mistake. That's my mistake. All right, so second type. Remember, yes, ma'am. Go ahead, Samantha. Reactant side. Yes, ma'am. That's exactly right. Okay. So type 2. We've done stoichiometry. Pretty easy, right? Nothing very difficult about it. This type is the one that's most used other than Hess's law. Hess's law and calorimetry are the two most used delta H calculations. This is the one that's pretty straightforward, but there's a lot of odd stuff going on with it, okay? So calorimetry, since we cannot know the exact enthalpy of reactants and products, we measure delta H through calorimetry, which is the measurement of heat flow, and here's why. Can you technically take a temperature recording device and put it on a reaction? You can? On the reaction. Yeah, but where do you know where the reaction is going on? It's so small you can't tell what's going on. Yeah, prime example. Let's go up here to the gas station, light a match, and drop it. If you use the laser pointer and I gave everyone else in here a laser temperature pointer, would everyone get the exact same temperature? Huh? Yes, exactly right. That's what you're telling me. So whenever we calculate delta H, we're not calculating delta H for a specific spot or specific location. We're calculating the delta H on average. We're calculating all the spots, which is exactly what temperature is, right? So if you think about, do all molecules travel at the same speed? So what you're telling me is that molecules should all have different temperatures. Why? Because they have different energies. But how do we record temperature? It's the average velocity of all the particles. Does that make sense? Yeah, so that's what we're taking the average of it. So here's the deal. So this is something called a bomb calorimeter, B-O-M-B. Okay? So what's going on is, if you notice, I'm going to show you a little bit clearer picture in a second. What is this outside looking gray thing? Read right there. It's an insulated container. It's normally made out of a steel box. Okay? What is the darker blue looking color? Let's see. I don't even know where that is. Yep, it's at the bottom. It is water. Okay? Well, what do we know about water whenever temperature changes happen? Water changes temperature, right? If it's absorbing energy, what happens to the water? It heats up. What happens if energy is sucked out of the water? It cools down. Okay, so what happens here is we have a negative and a positive and negative electrode, and then in here we have a cup holding the sample. What do you think the electricity is used for? To make it react, to make it burn, basically to set it on fire. Okay, and this is how they get calories for food. They take your Cheeto, they put it in this thing, and they set it on fire. Okay, well, what is this other little box inside of the water? This is the reaction chamber. It's a bomb. So what's going to happen when that Cheeto catches on fire? It's not going to blow up. What's going to happen to that steel box around the Cheeto? It's going to heat up. Well, what's going to happen to the water around that steel box? The water also heats up. Well, what is this little thingy? It's a thermometer. So what is the thermometer determining the change in? The change in the water temperature. So this is why calorimetry is a little weird. What are we wanting to know the energy change in? The water or the Cheeto? The Cheeto. We're trying to figure out what the Cheeto did. But how are we going to measure the change in the Cheeto? Through the water. So when you calculate Q, when you calculate the heat, which is absorbed or lost by the water, is it really what's going on in the reaction? No, it's equal but opposite. Now let's talk about real calorimetry for just a second. Do you think some of that steel box absorbs some of the energy that the Cheeto gave off? So is there an issue with that steel box? Does it allow all of the energy to escape into the water? No. And so there are some, and let me talk about real world application. There would be some ways you would have to calculate for a percentage of error because it's not going to be perfect. If I take this Snickers bar and I set it on fire, you'd be mad at me. Okay? But would it release some sort of energy? If I put it in this thing, what's that water going to do? You can set chocolate on fire, yes. Well, it does, but it does release energy. Okay? So this is what calorimetry is. We're going to calculate that green part. What's this green thing say? The measurement of heat, what? Flow. And the heat either flows out of the Cheeto or where? Into the Cheeto. Okay? So what happens in a strange, weird reaction, what happens if that Cheeto turned really, really, really cold? What's the box going to turn? Cold. Well, what's going to happen to the water? It's also going to turn cold. So where does that mean the energy is then going? Into the Cheeto. Because the Cheeto is going to suck all of that energy in, right? Okay? Kind of like Cheetos are super addicting. Yes, ma'am. There are some that have free calories, but none that have negative calories. Celery is a free calorie. Basically, your body burns more to dissolve it than it does that it actually puts in your body. So that's why free calories are good for you. I mean, you really will. Celery is like 98% water, and the other percent's... I know, that's awful. And the other part's water. So, I mean, it's water and cellulose, which is a fiber, which makes you... Okay? Next. Here's where calorimetry gets a little bit different. There are two types of calorimetry. Guys, we don't have equipment in a normal, regular chemistry lab that we can just use a bomb calorimeter. That's way too expensive. So the two types we're going to use the type we're going to use is what's called a coffee cup calorimeter. You literally take two styrofoam coffee cups and you stack them together. Now, do those coffee cups insulate fairly well? Okay, well, I mean, obviously, if you ever drink coffee, it's not going to burn you if you walk around with a styrofoam cup. What happens if you double insulate it? It's even better, right? So a coffee cup calorimeter in the lab, this is how we experiment to find the energy of a particular system. We use styrofoam reactants that begin with the same temperature and look for the change in temperature. After all the data is collected, and this is important, the mass or volume of water. Now, and again, I think this is a typo. I need to add this in right here. The mass or volume of water. And there's two little points of emphasis that I need to make on this. Number one is, why do we care about how much water you have in there? No. When we calculate Q, what are we technically calculating the change in temperature of? The water. So does the water amount matter? Yes. Let me show you the formula. So when we start calculating Q, we're going to have M CP delta T. You've all already told me that you're calculating the delta T of what? Of water. Well, if we're calculating the delta T of water, then what do we need the M to be? We need the mass of water. And finally, what about the CP? What do we need it of? We also need it of water. No. CP is specific heat. We'll talk about that in a second. Now here's my second point. The reason we need to know the mass or volume of water is because we're calculating the delta T of water. But, let me see how I want to ask this question. If you know the volume of water, or if you know the mass of the water, do you know the opposite? Write this down if you do not know this is a fact. I have stressed this several times, but it's one of those things that seems to flee everyone's brain. Good. This is something that's very crucial in this chapter, because I'm going to tell you, they will give you three different styles of information in one question. And you've got to be able to read through their garbage to get to the point. Because when you calculate Q, it was M times CP times delta T. You know how to calculate delta T. CP is a constant, but the M always throws everyone off. You need the mass of water. But will they always tell you, here is 10 grams of water? No, we don't do water in grams. How do we normally do it in? Liters or milliliters. So this is what you have to know, is when they give you this thing, what is its equivalent in grams? The exact same number. But here's the deal. Guess what? What if they give you 2 liters of water? Is it 2 grams? 2,000. Every year, students miss that problem because they forget to convert it over. They put 2 because they think it's a 1-to-1. They think it's a gram to liter. It's a gram to what? Milliliter. And that's the problem, is they give you liters of water, and you just assume that it's the same for grams when it's not. It's a multiple of 1,000. Okay? I can't stress to you how important this is going to be over the next few slides in the next day or two. Now, the last thing is, what if they don't give you milliliters? What if they give you cubic centimeters? Exact same thing. Yes. 1 kilogram of water is 1 liter of water. 1 centiliter? It would have to be meters cubed. 1 cubic meter is 1 kilogram, which is 1 liter. Everything moves. No, it would be 1 decimeter cubed. Yep, 3 places to the left. You with me? Okay, because gram is going to go to kilo, milliliters is going to go to liter, and centimeter is going to go to decimeter. That makes no. Is it no? Decameter, not deci. You got my brain working wrong. So, King Henry died. So we're actually starting starting here. So 1, 2, 3. So it's actually a hecta. Oh, I knew something didn't look right. Okay, this is much better. All right, so we're starting here and we're going 1, 2, 3. So it is a decameter cubed is 1 kilogram and 1 liter because everything is 3 places to the left. I think that's right. I may be wrong, but that's okay. No. You won't have to. You will never have. They'll never give you that. Okay. So you've got initial and final temperatures. That's just your delta T. We can use specific formula to find the energy released or absorbed. We refer to this process as constant pressure calorimetry. I yelled this yesterday. When things are at constant pressures, how are Q and H related? They are equal. Remember we talked about it. If you change the pressure, are Q and H equal anymore? No. Okay, so that's very important. So again, at these conditions, Q and H are equivalent. They're the exact same. So here's the second. Excuse me. No, I forgot this slide was here. By carrying out reactions in an aqueous solution. So my question is, what does aqueous solution mean? You've got some sort of soluble compound dissolved in water, right? And what form is that soluble compound in, Jacob? An ion form, right? In a simple calorimeter, one can indirectly measure the heat change for the system. Guys, these two words are very crucial. Indirectly and system. What is the system? It is the reaction itself. Can you put a thermometer on the reaction? No. So how do you measure the temperatures? That capitalized word. By indirectly measuring the heat change. And what source are we using to measure that heat exchange? The water. Okay? By measuring the heat change for the water in the calorimeter. So, when you calculate Q, it's important to note that the M and the delta T are what? Only for the water. Because the specific heat for water is well known as 4.18 joules per gram per degree Celsius, we can measure the delta H of the reaction with this equation. Q equals MCP delta T, which is exactly what I just wrote down. Now, I'm going to tell you now, put a big, huge circle around this number right here. You have to have this number memorized. You will be using that number a lot, which is the specific heat of water. Okay, CP is the specific heat of water. So to kind of summarize all calorimetry, the heat lost by the substance is the what? Heat gained by the water. Could you rewrite this in a different way and have the exact same meaning? How could you rewrite it? Very good. The heat gained by the substance, yeah, because you just restated it backwards. The heat gained by the substance is the heat what? Lost by the water. So when you read this, as it's written currently now, heat gained by water. In this blue form, as it's written, what would be the delta T? Would it get warmer or would it get cooler? Warmer, because what's happening to heat? It's being put into the water. What happens if heat was lost by the water? Delta T would be negative because it get colder. Does that make sense? Yes, no, maybe? Okay. So you're always calculating the Q of water because that's how the delta T is measured by the thermometer. So the final summary of this is very important. That when you calculate the Q of the water, what is the Q of the reaction? Equal but opposite. And how do you think they're going to ask you for the answer? Do you want the Q of the water or do they want the Q of the reaction? They want the Q of the reaction. So you've got to know this in your brain. When you calculate the Q of water, you've got to flip the sign to get the Q of the reaction. Is everybody on the same page here? Okay. Now, this is the fancy type. This is an actual real bomb calorimeter. It's the exact same concept as we just looked at. It's just a more fancy way to look at it. So weighed reactants are placed inside of a steel container and ignited, and is often referred to as constant volume calorimetry. Remember we talked about it a minute ago. What if pressure and volume are constant? How are Q and H related? They're the same, so it doesn't matter here. This is used by industry to determine the number of food calories that we consume. So on the Snickers bar that I have, it says that there are 250 calories in this one Snickers bar that I'm going to delightfully enjoy at lunch. So, how did they determine how much? They put it in that thing and set it on fire. Okay? It does sound scientific, right? And so what happened is they were able to determine the Q of the water, right? And then they were able to determine the number of calories. All right? So reactions can be carried out in a sealed bomb such as this one. The heat absorbed and again or released by the water is a very good approximation of enthalpy change for the reaction. Now here's something I want to point out. This word right here. Why is this word very important? It's not going to be perfect. Why? Because what will this steel box containing that reactant do? Will it hold some of the energy in? Yes, and so that's why it's a good approximation. So you're going to have a standard deviation there that's going to cause an issue. Because the volume in the bomb calorimeter is constant, what is measured is really the change in the internal energy, delta E, not delta H. For most reactions, the difference is very small. So again, delta H equals delta E plus P plus delta V. Since delta V is 0, then what is P delta V? 0. Therefore, H is equal to delta E. So since there's not going to be a change, they're pretty much equivalent. Yes, sir. Just put equals. Don't go that far. Yes, ma'am. You good? Okay. All right. So, again, enthalpy. And this is what we're going to talk about. This is a little bit more specifics. Terms to know. Heat capacity, specific heat capacity, and molar heat capacity. The one that we're going to focus on is the one in the middle. We're going to focus on specific heat capacity. So if you're circling or highlighting things, this is the one that you need to highlight. Okay? Because, again, when you calculate Q, what was that formula again? M CP delta T. What does the M stand for? Mass. So notice what this says. Specific heat is the same as the above, but specific to what? 1 gram of substance. So if you read what it says, the specific heat capacity is the amount of energy required to raise the temperature by 1 degree. Okay, it's the amount of energy to take any substance and raise it 1 degree. And here's the part where students every year kind of get confused. Is it can be in both Kelvin and in Celsius. Why is that acceptable? Because a 1 degree increase or decrease in both of those numbers doesn't matter what unit you're in. No, is 1 increase in Celsius and 1 increase in Kelvin the same exact change? So your delta will not matter. And here's why. How do you get from Celsius to Kelvin, vice versa, or either way? Add or subtract 273. Do you agree? It's an even swap. If it were Fahrenheit, would it be an even swap? Is 1 in Fahrenheit, 1 in Celsius? It's not. But it is in this, and that's why it's acceptable. So in some books, you will see it joules over gram degree K or joules over gram degree C. It does not matter. Go ahead. I've no clue. No clue. Yes. Okay. Now, molar heat capacity, you will see this occasionally. I've never seen it in a question, but it does show up. The same as above, but a specific 1 mole of a substance. Okay. 1 mole versus 1 gram. And again, I personally think, I don't know why they don't use molar heat capacity, but they do use specific heat capacity. All right, so here is a list of specific heats for 8 different things. Again, specific heat is the amount of energy required to raise the temperature of a substance by 1 degree. We define specific heat as, again, of 1 gram. And look at this chart. Of this chart, which one has the highest specific heat capacity? Water. So this bottom question, what does this table tell us about the specific heat of liquid water? It requires the most amount of energy for every 1 gram. Please write that down here. It requires the most amount of energy for 1 gram. It requires the most amount of energy for 1 gram. A long, long, long time ago, Did people use iron skillets to cook their food? Yes. Okay. Look at the two metals that are on this board. Iron and aluminum. So, a long, long time ago, back on the wagon trail, all you had to heat up your food was what? Well, but not as much. Fire, right? Does all fire only have so much energy? Well, look at those two numbers. Of those two, which solid metals would heat up faster with the same fire? Why would iron heat up faster? It has a lower specific heat. So does it make sense why iron is a better choice for aluminum for cooking substances? Because it requires less energy to heat up. Well, the more energy you put in, the hotter it gets. So that's why iron is used for a cooking surface and aluminum is not a very good cooking surface. Now, can you put it in there to help cook? Yes, but does it conduct the heat into the food? No, it's just basically to keep things from sticking, right? It's because it doesn't have a sticking substance. But notice what that is. Okay. Now, mercury liquid. Does it take a lot of energy or little energy to heat it up? Very little. What was mercury used to be for? Thermometers. Well, you stick that thing in your mouth, what happens to the mercury in the thing? It starts moving, right? Well, why does it start moving? What's happening to it? Heat them up. Well, when they start speeding up, what can the volume do? You can start expanding, right? It can start going up the tube. Well, that's why how long does it take for the mercury to start rising in those things? Pretty quick, right? Especially if you go from room temperature, which is about 73-ish, and your body temperature is 98. That's a big change, so it moves really, really quickly. What is what in Fahrenheit? One of them is 9/5 and one of them is 5/9. So you got to add and subtract. To go from Celsius to Kelvin, you add 273 and multiply by 9/5. To go from Fahrenheit to Celsius, you subtract 32 and multiply by 5/9. Yeah, it's weird. Why they came up with Fahrenheit, I don't really know. All right, so this is the last thing of the day. This was on the test last year. This was the exact question, the very last question, and I'm going to be 100% honest with you. When I read this question, I had no clue how to answer this thing. None of my students last year got any credit on this question at all because I didn't even understand it. And so I finally got to looking at it and I was thinking, all right, let's see if we can figure this thing out. So aluminum metal can be recycled from scrap metal by melting the metal to evaporate impurities. It's a pretty deep thing. Calculate the amount of heat needed to purify 1 mole of aluminum, originally at 298, by melting it. The melting point of aluminum is 933 degrees Kelvin. My first question is a delta T going to be a factor here? Yes. What was the original starting temperature? 298. And what was the melting point? 933. The molar heat capacity of aluminum is 24 joules per mole degree Kelvin. And the heat of fusion of aluminum is 10.7 kilojoules per mole. See how confusing this question is? So here's the answer. Just this top box. Okay? So, to raise the temperature from 298 to 933, Q is equal to 24 joules per mole, which was the what? The heat capacity, times 1 mole, times what? That was delta T. So you multiply all of these things together. So what is this really? This is CP, this is M, and this is delta T. It's the specific heat formula. But it's not given in mass, it's given in what? Moles. You see the difference here? So this is not the specific heat, this is the molar heat. This isn't the mass, it's the what? It's the amount of moles. Say that again? What do you mean, can you do that? You can. And I didn't know that until this question, which is why I hated this question. But not only did you have to know how to calculate this, then look what else you had to do. You had to then add the 10.7 to it. This is a ridiculous, ridiculous question to me. Some people say it was easy. Some people said it was hard. I never knew. And so this is the kind of the summation of this. Is there's two different versions of Q. You've got Q is equal to mass times specific heat times delta T. And then you've also got moles times molar heat times delta T. Those are the two different ways that you can calculate Q. And I had no clue about this bottom one until last year. So I'm learning as you guys are learning as well. This is only my 5th year doing this. And so we're trying to get there. So tomorrow we'll come back and we'll look at the second part of this question to make sure we're kind of all on the same page.